In these two videos, I'm going to show you the 8 skills that every student needs to succeed in chemistry. And so let's get started with the first one, unit conversions. This is where you always start. So when you do this, I hope that most of these you can do in your head. But when you're converting units, let's say you kind of forget which way to go, always multiply by a factor that will trade in the unit that you have for the unit that you want. And so here I've got kilograms and grams. Kilo means 1,000. So 1 kilogram is equal to 1,000 grams. So when we multiply, the units cancel and we get 450 grams. Now remember, keep your sig figs the same. Whatever you started with, you end with in sig figs. Now let me show you another one. What if you get something like this? You look at this and say, what is that? Well, you recognize mole, and what could this little m be right here? That has to be a millimole. So what in the world is a millimole? Well, we've got to trade in millimoles, so let's put that on the bottom, and let's go to something we're comfortable with on the top, moles. So what would a millimole be? Well, milli is defined as 1,000th, so a millimole is 1,000th of a mole. So we would divide that by 1,000, and we would get 0.055 moles per liter. Looky there, that looks like molarity. So this would be 0.055 molar. And so that's just a way of showing concentration. So I hope you can do those conversions. Next, the periodic table. It is loaded with information. So let's look at some of the things that you can determine. First of all, you've got the periods. We've got 1 through 7, and they're often labeled down the side. Then you have the groups, 1 to 18. Some of the groups have special names. We've got the alkali metals would be the first group. Then the alkaline earth. Way over here we have halogens, and then noble gases. The next thing would be the blocks. This is the S block, those first 2 groups. Then this is the D block, transition metals. The P block is this group right here. And then we've got the F block, which we really don't deal with too often. So we've got the blocks. Then also electron configuration is something that you can see from the periodic table. So everything in that first group is going to end with something S1. The second group, something S2. This would be D1 over to D10, P1 over to P6, and then we've got F1 to F14. And so you can look at the periodic table and determine the ending of the electron configuration. Now, with that being said, we also have valence electrons. So let's look at that. And you know how we get valence electrons, right? Those are the electrons that are in the outermost energy level. And so valence electrons, we'll just label them up here. 1, 2, skip the transition metals, 3, 4, 5, 6, 7, and then we've got 8. Of course, helium is different. He's only got 2 electrons total. So valence electrons. Now, we're also going to use valence electrons to predict ion charge. So the elements with 3 or less are going to give those away. And so our ion charge would be 1 plus, 2 plus, and then 3 plus. Then the elements over here with 5, 6, or 7 valence electrons in those groups are going to gain electrons to get that full octet. And so these would be -3, -2, and -1 charged ions. So that is a really easy way to memorize the ion charge that certain elements would form. All right, then let's move on. Trends, periodic trends. Okay, one of the big trends would be atomic radius. And radius is going to increase down toward francium. Francium is the largest element. And so as we go down a group, they get larger because we're adding another energy level. And then as we go to the left, they're going to get larger. And it has to do with effective nuclear charge. Now, the other 2 trends are the opposite. So ionization energy and electronegativity do the opposite. And so as we go across a period, they both increase. This is electronegativity. And then also as we go up a period, they increase. And so we're looking right here with electronegativity and ionization energy. Okay, so they go like this, and they're opposite. And the good thing about this is you can remember one trend Okay, radius goes this way to francium, and then the other trend goes the other way. And you're going to need to use those trends to compare some of these properties of different elements. All right, let's keep going. Stoichiometry. Wow, we love this, right? You've got to be really quick and good at stoichiometry. So balancing equations, I know you can do that. And then stoichiometry problems. So here's one. We start off with a given amount of methane. And then first step, you always have to get to moles. Always. And so how do you get to moles? Well, trading your grams of methane for a mole of methane. That's molar mass. And for methane, that would be 16. Okay, so I've got 2 moles of methane. Now, at this point, you can go anywhere else in the reaction. You can go to any other product or any other reactant. And so in this case, we're going to go to oxygen. That's what we're looking for. And so let's use a mole ratio. I'm trading in moles of methane for moles of oxygen. Now you go to the reaction and grab the coefficients that are in front of those elements. And so 2 oxygens for every 1 methane. All right, now we end up in moles of oxygen. We can go to grams of oxygen. We can go to liters of oxygen. We can stay in moles, wherever we want to go. So in this case, we would trade in moles of oxygen for grams, and that would be molar mass of oxygen is 32. Remember, it's diatomic. And so we would end up with, let's see, we'd have 128 grams of oxygen. And we can go anywhere with stoichiometry. Okay, so this is the basis, right? You're going to use 2 things. You're going to use molar masses, which you know how to do. Just add up the masses of all the atoms in the formula. And then we're also using mole ratios, okay? And these are you're going to just grab these out of the reaction and use the coefficients from the reaction. Okay, one more thing I want to show you about stoichiometry is when it comes to energy. So take a look at this. Let's say we started off with 0.2 moles of, let's say we do oxygen. Let's say oxygen was consumed. How much heat is produced? So here's the thing about when you have an enthalpy change given with a reaction. It is for the number of moles exactly as written. So that 880 kilojoules is produced when 2 moles of oxygen react. Well, we don't have 2 moles, right? We have 0.2 moles. So what we're going to do is we're going to use that as a ratio. That's how many kilojoules per, go to the reaction, 2 moles of oxygen. Okay, so this is super easy, right? And so how many moles? That is, the moles cancel, we're left with kilojoules, and so that is 88 kilojoules will be produced. Okay, and so you treat that enthalpy change just like you would another reactant or product. All right. Next, bond type. All right. In chemical formulas, they all look alike, don't they? The atoms and the subscripts, they all look alike. So what you have to do is there are 2 types that you need to look for. And we've got ionic, and that's going to be when you have a metal and a non-metal bonded together. And then you have molecular compound, and that's when you have 2 non-metals bonded. Now, we're also looking for polyatomic ions, and you just have to be really familiar with those when it comes to chemical compounds. So first thing I'm going to look for is polyatomics. That is nitrate. I noticed that one. And then I have another one down here, and that is ammonium. Okay, now ammonium is a ion that is a nitrogen and 4 hydrogens covalently bonded together, but overall it has a charge, and so this one is ionic. All right, sodium nitrate, ionic. Now, gotten rid of all the polyatomics. Now, what are we looking for? I'm looking for metals and nonmetals, and the metals will be written first. And so the first compound, I have sodium, and then that's a metal, and then fluoride, nonmetal. So this one too is ionic. All right, we come to the next one. Carbon is a nonmetal, fluorine is a nonmetal, and so this is a molecular compound. Okay, then the next one, I have nitrogen and oxygen, both nonmetals, and so that would be molecular. Hydrogen and fluorine, both nonmetals, and so that is molecular. Now, why does it matter? There are different rules for naming ionic and molecular compounds. For ionic compounds, you name the cation and the anion, and that's it. Molecular compounds, you're going to use prefixes to tell how many elements or atoms are in the formula. So ionic and molecular is a big deal because that also is going to predict physical properties and solubility and all kinds of things, future topics in chemistry. So first of all, when you see a compound, you need to think, is this ionic or is it molecular? I hope that helps. That's 4 of them. I've got 4 more to go in the next video.